G'day and welcome to today's video. I hope this video finds you well. As I ramp up my preparations for the teaching semester here and for online delivery, I thought I would experiment with my home office setup by presenting a video on some recent results that we've obtained. So instead of just creating random content, I thought I'd have a go at explaining some results that we found very interesting and also that I've over the years found particularly helpful. So the topic for today's video is the Haar measure, and in particular the Haar measure over the unitary group. So the Haar measure over the unitary group is usually written as the integral du of some function of u. Here u is an element of the unitary group of d by d unitary matrices. Now, these kind of integrals pop up all the time in all kinds of places, often when you least expect it. And often you have this problem that you want to calculate one of these integrals. These integrals have very many beautiful properties, but in practice, often you just want to calculate one given integral, and you don't have the good luck that you can find the result anywhere with an easy Google. So the kind of integral I'm talking about that often turns up is something like this. So you are doing some project and you're looking at random matrices, and then you want to take an average over all possible random matrices of some function. In this case, we're thinking about the function trace of u squared, the absolute value squared. This kind of thing pops up all the time. Now, Haar measure, you want to take this kind of integral with respect to Haar measure. So here I denote Haar measure by du. So what is this Haar measure? Before we get along any further in this video, what I'm going to do is briefly summarize at a heuristic level its definition and also some of the basic properties. So to understand Haar measure, you should think of the unitary group. You have to, it's helpful to have some kind of picture in mind. The picture that I usually have in mind when I think about the unitary group of d by d unitary complex matrices is something like this, right? It's like something analogous to a sphere. So I'll put big scare quotes around that. And Haar measure is like the uniform probability measure on this manifold. So we've got the manifold of d by d unitary matrices, and Haar measure is like the uniform probability measure over this manifold. Now, Haar measure has it's not just any old measure, it has some very beautiful properties, and the properties that are most important or relevant for today's video are left and right and invariance. Under shift. Under shifts by multiplication by an unitary operator v. So suppose that v is a fixed unitary operator, then it's the case that if you have an integral such as you've got some function f on this unitary group, so f maps from the unitary group of d by d unitary matrices to something else, right, to some other space. I don't know, we'll call it M. And what does it mean for the Haar measure to be left or right invariant? Well, suppose instead of this integral expression, you had something like the following. So you got integral du f, and then you've got this fixed unitary here, v, and it's multiplied by the argument of f. And so suppose you have this kind of integral. Then to make this somehow simpler, you might shift by making a change of variables. So to do that, we just define a new variable, let's call it u dash, and that's just v times u. Now, of course, whenever you change variables, especially in a multi-dimensional integral such as this, you have to multiply by a Jacobian factor. However, Haar measure has this very beautiful property that if you do make a shift, So if you have du, well, you integrate over u, then this measure is exactly the same as du prime. In our case, we have to multiply on the left to get back our original u. But this, because we're multiplying on the left by a fixed unitary operator, we know that the Haar measure, or one of the defining properties of the Haar measure, is that it's invariant under such left multiplications by arbitrary unitary operators. So we actually have, there's a prime there. Now we actually have that the integral with respect to du is really the same as the integral with respect to du prime. Also we have, and that's so-called left invariance, also we have right invariance. So we also have that operators multiplying on the right by a fixed unitary operator v gives exactly the same measure again. So this is really the most important property of the Haar measure, and the one that really we make most use of in the rest of this video. So let's review, we've got ourselves an integral over the unitary group that we want to calculate, and we have a function on the unitary group, and well, why don't we just calculate it? Well, it's combinatorially somewhat involved to do these integrals in general. There is in fact a very beautiful formalism to completely calculate an integral with respect to the Haar measure of the unitary group. You can find it in this fantastic paper of Collins and Schniardi from 2004. And here they have a completely general expression for how to compute a measure, an integral with respect to Haar measure over the unitary group. Now, the problem with this very beautiful paper is that the answer is complicated. The general answer requires evaluation of something called the Weingarten function, and that's not something that we would really want to get into in casual applications. So typically we don't want to compute such a complicated Haar measure integral when we want to compute these things. In practice, in anger, usually the integrals that we want to calculate look more like this one here, integral of du of the trace of u squared, or perhaps something to the power 4. So that's the goal. We want to compute this kind of integral, but we don't want to, we don't really want to decode the formula in this otherwise wonderful paper of Collins and Schniardi. This has often happened to me that I've wanted just a specific Haar measure integral, and I've been too lazy or too unmotivated to actually go through the details of this general formula and how to apply it. Instead, what I'd really like is some kind of method that's sort of practical. What we'd like is that this method is somehow practical for commonly occurring cases. We'd also like that this method is perhaps elementary. And what do I mean by elementary? Well, I mean here that it uses just linear algebra and calculus. And even though it's elementary and practical, it might not be easy to remember, but I'd prefer that some method that we use be easy to remember, because I don't want to have to look back in complicated notes to remember factors of d or n or whatever, factors of 2, whether or not they're there or not. So today, the goal of this video is really to present to you a method that achieves these 3 goals. It's practical for commonly occurring cases, so you can actually do it. It's elementary, so it really doesn't use linear algebra and calculus, and it is somewhat easy to remember. And you can find this method in an appendix of a paper that we recently uploaded entitled No Free Lunch for Quantum Machine Learning. The method's described in an appendix to this paper, which you can find starting on page 5, I believe. Yes, page 5. But instead of talking about the no free lunch theorem today, I just want to talk about this method, because I felt that this was something of sort of independent interest that might be also fun to look at in other contexts. This I should say before I go on that this approach is based on sort of a long series of conversations and collaborations that I've had with Aram Harrow and Matt Hastings over the years. Matt Hastings brought this a slightly more general method to my attention based on what he called the Schwinger-Dyson equations, and then Aram showed me a somewhat simplified way to do these computations. And then by introducing tensor networks, I found for me, was the simplest sort of easy to remember way to apply this idea. So what we're going to do is I'm just going to explain the method for one key example. And then once you've seen it for this key example, then that should be enough information to really help you apply this method to more complicated examples. And so the key example that I'm interested in today is the calculation of an integral which I call S2. So what is S2? S2 is the integral over the Haar measure over unitary group of the following function, u dagger tensor u. So that's the key example that we want to study today. How do we compute this integral S2 over the unitary group of this strange tensor product argument, u dagger tensor u. So my claim is that you can do it, and then when you do it, you'll get an answer, and the answer will be 1 over d times by the swap operator. That's the answer. But what I'm going to show is the method, how I used to arrive at this answer, and further I'll explain why S2 is useful to calculate the integral I originally quoted at the beginning of this video, namely the integral of trace of u squared. Absolute value trace of u squared. So the first step is to exploit the information we have. So we know we have a Haar measure. Haar measure is invariant under left and right multiplication by unitaries, and we're going to exploit a little bit of calculus. So we're going to do a change of variable. And the change of variable will be to replace u by v times u. So u in the argument of this integral gets replaced by v times u, where in order to use some calculus, v will be of the form of e to the I epsilon x for any x which is Hermitian. So you can quickly verify that anything of the form e to the I epsilon x, where x is Hermitian and epsilon is some infinitesimal, that's some positive infinitesimal, that v is always unitary. Anything of that form is unitary. So we're going to make this change of variables. U goes to v times u. So we take our original expression for S2, that's the integral du, u dagger tensor u. We now make this change of variable and exploit the invariance of the Haar measure, and then we obtain the following representation for S2. So we've made our change of variables, and we end up with this expression for S2 after making the change of variables. So technically I should put a prime over the u's everywhere here. I'm going to quickly neglect that and just write u again, right? So sort of to help the notation from getting too cluttered. So by making this change of variable by multiplying on the left by e to the I epsilon x, we get a different way or a different expression for S2. It's exactly the same. These two expressions are in fact equal, right? Because of the left invariance of the Haar measure. Now we've got two expressions for S2, and we've got an infinitesimal. And so whenever you see an infinitesimal, the first instinct should be to exploit Taylor's theorem. So we're going to Taylor expand. That's our next step. I think that's reasonably elementary. Second step, here it is, Taylor expand. So we know that e to the I epsilon x, the first order is the identity plus I epsilon x, plus of course this higher order stuff which we're going to neglect for this video. And we're going to employ this approximation and expand the integrand to first order. So if we put this approximation via Taylor's theorem into the integrand, then we have the following Taylor series. So we get integral du, and now we must Taylor expand this e to the minus I epsilon up there, so we get identity minus I epsilon x. We're only going to keep things to first order, so I'm going to immediately just drop that, all higher order terms, and then I'm going to expand the second tensor product argument and get this expression here. So S2 is approximately equal to that. Now if you sort of multiply everything out and retain to first order, you get a very interesting result. So to zeroth order, we get back S2, right? That's the thing we started with. And then we also end up with a second expression. And that second expression looks like this. We've got integral to u dagger x tensor u plus I epsilon integral to u dagger tensor x u. Now, remember, the left-hand side and the right-hand side are, well, they're equal in the first line to order epsilon. What does this mean? And since S2 appears on the left-hand side and the right-hand side, well, S2s have to cancel. And so the consequence of this is we learn that to first order, the following identity must be true. I'll factorize this slightly. I'll write this as I epsilon identity tensor x integral to u dagger tensor u, and then on the right I will write a minus sign, and then I epsilon, and then we got this integral to u, and now the u dagger tensor u again, and then on the right we've got this x tensor I, right? X is Hermitian, right? There's no dagger. So we've got this identity that this integral, which we recognize also as S2, sort of commutes in a twisted kind of way with the operator x. And so now we'll just rewrite slightly this identity, and we're going to learn, I think, probably the most important piece of information for this method, namely that S2 times by x tensor the identity equals the identity tensor x times by S2. Now, what's very beautiful about this particular result is that it's true for all x Hermitian. This is not just true for a given x, it's true for all x. So now we come to the third step. So that was the second step. Now we come to the third step. Since this is true for lots and lots of x's, we're going to apply it for some special x's that we like. So the x's that we like here is we're going to choose x in turn to be each of operator basis of d by d Hermitian operators. So we'll let x be in turn lambda to the power alpha, where alpha runs from 0 to d squared minus 1. What are these lambda alphas? They are matrices, right? They're just d by d complex matrices that we're going to take them to be Hermitian, and we're going to take them to be orthonormal with respect to the so-called Hilbert-Schmidt inner product, meaning that if you multiply two and take their trace, then you get nothing unless alpha equals beta. Okay, these are the properties of these matrices. And then we're going to take our identity, which we'll call star, and we're going to multiply it. So we take star, we multiply on the right by lambda alpha tensor the identity and then we end up with the following equation that's certainly true, namely lambda alpha tensor times by lambda alpha tensor the identity equals the identity tensor lambda alpha S2 lambda alpha tensor the identity. So this is true for all alpha, right? Because it's true for x. Substituting x as lambda alpha and multiplying on the right, it's also true. So then we just take the sum of this true identity. So we sum over alpha. And then we end up with the following expression. We get the sum over alpha of S2 lambda alpha tensor the identity equals the sum alpha of identity tensor lambda alpha times by S2 times by lambda alpha tensor the identity. So this is a true statement. Now it turns out that this sum simplifies in a very nice way. So the thing to bear in mind here is that there is a neat identity for sums of lambda alphas. And here is the neat identity. It turns out that the swap operator is exactly the sum over alpha of lambda alpha tensor lambda alpha. Remember, lambda alpha is Hermitian here. How can you prove this? So how would you argue that swap is equal to the sum of these operators? Well, let's try and calculate the coefficients of swap as an operator with respect to this basis, complete basis, orthonormal basis of Hermitian operators. So what we want to do is compute the coefficient C alpha beta of the operator swap with respect to this operator basis. And then we have this neat trick, right, that if you have trace of the tensor product of two operators times by swap, it's really just the trace of the product of the operators, which of course, according to the defining property of this basis, is delta alpha beta. And so that tells us that swap, when we express it in terms of this operator basis, has this expression here. But we already know, of course, that C alpha beta is delta, and so that's how we arrive at our representation for the swap operator. Now, the beautiful thing about this particular representation for the swap operator is that it allows us to derive a whole bunch of other identities. And so the way we're going to do that is exploit some basic tensor network diagramology. So the way we do here is we represent operators by blobs with two legs. We represent vector spaces by lines and the action of various operators as tensor networks. Now, what we've got here, using a sort of primitive tensor network representation, is we've really got the swap operator, which takes the first subsystem, swaps it with the second subsystem. We've got that that's equal to a sum of a tensor product of operators. Now, that's what our identity star star actually tells us. It tells us this tensor network diagram here is true. So identity star star is, oops, I've actually called it identity star. I'll call it star star from now on. So the neat identity about the swap star star in terms of tensor network diagrams looks like this one here. Now, we can use this tensor network diagram to derive a whole bunch of other identities. And really nice derive other identities. So one thing we can do is we can always take a true identity and we can hook up legs, right? We can join legs up together. So we now know, just by looking at the diagram above, that if we hook up the output to the input of the second tensor product factor, that we have this identity here. This is easy to derive from applying, or from wiring together outputs and inputs. This is just a straight up consequence, right? But now we've got a loop, a contracted loop has the value d. So we get that d times by the identity is equal to the sum of alpha of lambda alpha times by lambda alpha. So that's really interesting because that's the thing that appears on the left-hand side of the identity that we're trying to calculate. Now let's go back to our fourth step, which is to apply these tensor network identities to our formula, which we'll call star, star, star. So our formula, triple star, in tensor network diagrams, as a tensor network, looks like the following. It looks like we've got a summation of alpha, we've got this S2 operator, we've got lambda alpha, remember S2 acts on two tensor product factors. So the triple star identity looks like this. On the left-hand side and on the right-hand side, we've got a sum over alpha of S2 lambda alpha And then we've got a lambda alpha coming in on the second tensor product argument in front of the S2. Now, applying the identity that we've just derived here, and also the swap identity to the right-hand side, will give us a pretty neat expression. So just applying the identities we've already derived, we'll learn that the D times by S2 times by, well, the identity, right? Because when you sum over lambda alpha twice, you get D times by the identity, has to equal something here. And we've got to sum over lambda alpha twice, and we're going to apply our first identity to the second argument here. Now remember, the sum of lambda alpha, tensor lambda alpha, is the swap operator. So that means this argument comes over here and gets pushed into there, and this argument goes under, gets swapped with that one there. And then if we look at this identity a bit closer, then we see that we've got D times by S2 equals something kind of funny, right? We've got this crossed over tensor here. So, and we've got really an identity operator which takes the bottom subsystem to the top. So our final goal is really to study this strange crossed over guy here, that I've circled in blue, and derive an expression for that. But that turns out to be really easy, because we just use the definition of S2. So S2 is an operator which acts on two tensor product subsystems, and it's defined as the following integral over Haar measure. Now, to get the diagram that appeared in blue above, what we have to do is wire the output of the first leg into the input of the second. Well, let's do that on just the defining representation for S2, and then we see something really very simple and very neat happening. We get the integral of du of, well, first u dagger multiplied by u, but u's unitary, so u dagger times u is the identity. So then we have the integral with respect to u of the identity. Now, something I didn't mention at the beginning of this video is that the Haar measure is normalized to 1, so we just get that that's the identity. And so now, exploiting these identities all together, we can rewrite triple star as follows. Triple star says that D times by S2 is equal to nothing other than the swap operation. So what we do is we substitute in the identity I've just shown above into this blue expression here, and you can see that that just replaces S2 with a line, and then we have the result that we want, which is that S2 is, when we divide by this factor of D on both sides, 1 over D times by the swap operator, which is exactly the identity we wanted to show at the beginning of the video. So let me just scroll up to see that that's indeed the claimed identity. Yep, there it is. S2 was meant to equal 1 over D times swap. And we've just shown that using the properties of the Haar measure, calculus, and some linear algebra. Now, there's one thing that to finish up this video I should argue, and that is that this is actually a useful result to calculate, say, a whole host of Haar measure integrals that turn up in practice, including this one where we integrate the trace of u, the absolute value of u squared over the unitary group. So what on earth does this integral equal? Well, we don't know that, but what we do know is that the integral with respect to u of u dagger tensor u, now that integral is something we do know now. That's 1 over d times swap. Now, the way to get the integral we want is to just take the trace of both sides. And then you see the left-hand side simplifies in a very nice way to the trace of u dagger times by the trace of u. That's the integral we want. We'll call this integral I2. So we've got that I2 is this integral here on the left is equal to 1 over d times by the trace of swap. Now remember, the trace of swap is d, so that's just 1 on the right-hand side. So we have calculated that I2 is the trace of swap divided by d, or in fact 1. So that's how we can use this identity to compute the integral that we wanted to in the first place. Now, this method might look a bit special for this identity S2, but it also applies, I mean, it's a little bit more tedious to other integrals over the half measure. Another one that we cover in the appendix to our paper is this integral here, u tensor u dagger tensor u dagger tensor u. This has 4 tensor product factors. And applying exactly the same ideas as we did to calculate S2, you can also calculate this integral here. It's slightly more complicated. There's some more swap operators and more cyclic permutations going on, but otherwise the method is exactly the same. So I hope that you enjoyed this video. Best wishes and from me, and goodbye.